Thanks. All right. Are there any questions? Actually, if there are questions, we can we can discuss them as we go through the review. All right. Are there any questions if I start? All right. So today we're gonna talk about Wilson-Fisher fixed point as an example of a normalization group, connecting with some of the ideas of effective action and Kalman-Semanzik and beta functions that we've been discussing. But before that, as usual, we start with a review of the previous lecture, which was 8, not 7. All right. So recall what the Kalman-Semanzik equation was. We wrote the Kalman-Semanzik equation for the connected endpoint function. So these are the positions where we have inserted our operators. It's often, so I'm just gonna make a whole bunch of comments as we go along. It's often easier to write down everything in dimensionless parameters, right? So if there is an explicit M dependence here, you could think of that as, right, these are dimension full parameters. So you could always extract out a single single scale out of it and write these down as dimensionless parameters. Does that log from inside? Okay. Or you could think of these as some angle variables, right? This is the renormalized coupling, and this is the renormalization scale. This should be invariant under RG transformation, right? Under RG transformation, well, we described that. And this is the Kalman-Semanzik equation. Gamma comes from the wave function renormalization, right? The renormalization of the fielder operator. These, if you recall, these are beta functions. They're running of the coupling as a function of scale. This is explicit M dependence, and these are the expressions we had. We said that we could include mass terms in the story, treating it as a regular coupling because a scale invariant theory is going to be a fixed point, and scale invariant theory is not allowed to have a mass term, right? So it's going to be treated the same way as any other coupling. There will be a gamma. There will be a gamma factor sitting in front of it, right? And it's the point was that in arbitrary dimensions, this was a relevant coupling, right? So Kalman-Semanzik is the statement that renormalized correlation functions are invariant under the RG transformation. Good. In fact, all physical observables, including the S matrix and the effective action, should be invariant. Why? Why should the effective action be invariant? What does the effective action calculate for you? Sorry? Yeah. So it's the 1 PI diagrams for renormalized field. So that's something physical, right? That's why it has to be invariant, and it satisfies this equation. So it's up to you. It's up for you guys to figure out why there is this additional term. There's an extra term, but these are just the good old terms that we had for Kalman-Semanzik. There is this extra term. Yeah.
Why there is no gamma term for the S matrix? Kalman-Semanzik.
That's also another good question. Any thoughts? Where does the gamma term come? Where was the gamma term coming from?
Yeah.
Right. So it was coming from the fact that there was the correlation function had dimension of mass, canonical dimension of mass, right? The S matrix, however, is it's a dimensionless problem, right? So that's why. But it's good. It's a good exercise for you guys to derive these, right? If you want to get a good grasp of what a renormalization group is, how are these transforming? All right. We talked about composite operators that we were just discussing. So we said that an arbitrary operator O of M will have some sort of a transformation under RG like this. And if it's for example, if it's like phi squared term, this renormalization factor might not be z of phi squared. and the difference between the two would contribute to what we call anomalous dimensions. Now, when is this equal to z of phi of m squared? When is it equal? In a free massless theory, we said that it would be equal, and phi squared in that case was defined using normal ordering. Right? That was the case where we discussed this. That's a free fixed one. What we're interested in this whole course is we're interested in interacting theories. So if we're talking about interacting theories and we're talking about perturbation theory, right? We're supposedly interested in cases where this is no longer holding. Right? Anomalous dimensions. Yeah, okay, so I said that. Now, if there's an operator in general, if there is no under RG, it will mix with all the other operators unless there's some sort of a quantum number or some symmetry that forbids it, right? Symmetry forbidding it means that they have different quantum numbers, right? They transform under different representations, stuff. Good? So from Kalin-Simanzik, the lesson is that you could define gamma of O, the anomalous dimension, as m del m of ln of z of O of m. And we saw that explicitly that, for example, if you take phi n under Rg, these two-step transformations, if when b is near 1, it transforms as b to a power of n d classical. D classical is just the scaled is the free trivial scaling dimension of the field phi, which is d minus 2 over 2, exactly, right, for a scalar field, right? So this is the anomalous dimension, which tells you that how does the field scale differently compared to the canonical dimension, which is phi for n, phi n would be n times d minus 2 over 2, right? And remember just naive dimension counting analysis. Good. We talked about the solutions of the Kalin-Simanzik equation, and I'm gonna explain it a little bit with a little bit more detail this time. So let's first talk about Kalin-Simanzik is written for correlation functions, right? So let's just focus on the 2-point function as we did last time. We use this analogy of Sidney Coleman with bacteria growing in some pipe, right? But now I'm not gonna summarize that anymore. I'm just gonna say a consequence of it. It's just a characteristic method for solving PDEs, right? The 2-point function is gonna be a function of the ansatz we had for it was minus I over p squared, right? Some function Cayley G of p over m. That was the ansatz that we had, right? Now, as usual, we're gonna keep track of this parameter. It's easier to keep track of this parameter by introducing some t, and the reason for this t is like also clear in analogy with the bacteria example, right? So it's literally time over there. All right, with this change of variables, notice that the external 2-point function is only a function of a single variable p, right? In Fourier space, it's just a function of p alone, right? That's why I only have one variable. If I was doing a normalization group for higher point functions, what would replace this? Well, we'll get there, but think about that in advance, right? So in this example, what you end up with is del t, right? This log is there so that this is del t, right? Minus beta of lambda del lambda plus f lambda. And this was just 2 times 1 minus gamma of lambda. Do you remember what this term is for? This is just a dimensionality of this G2, right? We said that when we talk, well, anyway, just it's good to, every time you see these expressions, it's good to just analyze them again. This comes from the fact, to explain this, I said that we wrote down Kalin-Simanzik for dimensional full couplings, then we wrote it down for dimensionless couplings, right? Anyway, in the UV, which in this example would be P equal M, T equals 0, we start with some value of the coupling, right? I'm gonna call that lambda bar of 0 and lambda. Lambda bar is the function that tells you how the coupling, what the coupling is as a function of scale, as a function of t, right? So by definition, lambda bar of 0 and lambda is lambda. That's normalization condition, right? At p equal m, I set this, I've tuned my variable, my coupling to be lambda. To solve this differential equation, we said that the characteristic method tells you that you first have to integrate the beta function. You have to find the couple, the running of the coupling, which is solve this equation. Once you find this, which is now you know the coupling at every scale, the 2-point function will be minus I over p squared, some function to be determined, right? E to the power of minus 0 to t dt prime of f. This is the term that's coming from wave function normalization, right? It's multiplying the whole thing. It's telling you about the growth of the bacteria along the pipe, right? And this is telling you where the colony is moving to, right? Now, this function could not be determined using RG equations. It depends on the theory, right? From the structure of Callan semantic, you just can deduce that it will have the following structure, that it will be e to the power of an integral of something that has to do with gammas, right? That coming in an exponent, and that's about wave function normalization. As you run towards the IR, the size becomes larger, or like it changes as it changes, right? And this is the value of the coupling. We figured that out. But this, to compute this dependent, you really have to take your action and do perturbation theory in lambda and match the expansion of this term by term. So for instance, we normalize the theory so that at t equals 0, G2 of lambda bar is just 1. When we're expanding around small lambda bar, right? When lambda is small. But this term, to calculate what the dependence of G2 is, you have to do perturbation theory to higher orders, right? There's no way around that. We non-perturbatively wrote the formal form of the RG equation, solution to the RG equation, but that doesn't mean that we know the answer, because of course it's theory dependent. For that, you have to solve the theory. Oops. Good. Is it clear? All right. Now 4-point functions. Now 4-point functions, if you have a 4-point function, there are 4 incoming legs, right? We saw that in perturbation theory, for 4-point function, the scale that's relevant is the center of mass, right? So that's S variable, Mandelstam variable. We often did renormalization in a setup where we were looking at S equal T equal U, right? Equals some scale mu squared, for instance. So for example, I can renormalize by the condition that pi squared or mu squared and pi dot pj is equal to 0. Remember that at my fixed point, these equations could hold because masses are 0. All right, so this is the thing I'm gonna do. Previously, my 2-point function was a function of t, p over mu, right? The only variable I was dealing with. Now it's going to become its dependence on scale is going to be about this dependence on mu squared, right? So the Callan semantic, so G4 of mu 4, I'm going to write it as I over mu 2 to the power 4 minus I lambda, right? This is the analog of saying that at my renormalization scale, right? So when I wrote G2 is this, where was it? Well, let me just write here. This is the analog of saying that I wrote G2 as I over P squared, right? G2, but here when I put, this was 1 at P equal M, right? So this is this is a function of T, right? Indirectly, it's a function of lambda bar, right? But when T is equal to 0, this term is 1, right? That's my normalization condition. This is similar to that. right? So instead of p squared here, because you're dealing with a 4-point function, I'm just gonna put this scale. That's my scale of interest. G4 is dimension full, right? And that's my renormalization condition. Good. Now, if you just go through Kalin-Simanzek, you end up with mu del mu minus beta lambda del lambda plus 8. Oops, is this minus or plus? Whoops, I think it's plus. Plus 8 minus 4 gamma lambda of G4 of mu squared and lambda is 0. The role of T is being played by mu squared, right? That is the scale of interest. This 8, again, has to do with the fact that this guy is dimensional full. Right? So you could formally, using this bacterial analogy or method of characteristics, you could write down the solution to this. What is it? It's 1 over mu to the power of 8, some function that cannot be determined using general analysis. It depends on the theory. E to the power of 4, integral 0 to t. This is just a good old thing that we had, right? 2 times 1 minus gammas. But to solve this lambda bar, you have to solve beta functions, right? So you solve beta function, integrate beta functions, you find the couplings along the flow, and then you plug them in. This depends on the theory, of course. Good. And of course, as before, the way that we had G2 of lambda bar for small lambda bar was 1 plus order lambda squared, lambda bar squared, is we have this equation. Any questions? So this is a summary of what we did before. What we're gonna do today and on Thursday we're gonna be doing 2 examples of this in a lot more detail. The first example is going to be very much motivated by statistical field theory, the theory of critical exponents, which I was too quick about last time. I think I'm going to try to explain that a little bit better, right? The second, so that's going to be the ON model, right? And it's going to be about the Wilson-Fisher fixed point. I'll try to explain a little bit of the history of it, history behind Wilson-Fisher fixed point, why it's important, and the magic of large N. The message to take from here, is large N, the role of large N, right? Or epsilon expansion. Then the next, on Thursday, what we're going to talk about is another class of examples that are very important in physics. They're nonlinear sigma models. And I'll explain why they're important and what role they play, right? There are also another example where we could calculate these beta functions, right? These beta functions it's not like you can pick a theory and calculate them. By the way, I asked this before, beta functions of QED, right? In QED, what is the coupling? E, electric charge, right? Does it grow? Is it relevant or is it irrelevant? It's a relevant deformation. So it grows in the infrared, right? Okay, I'll just keep that. Is it relevant? Are you sure it's relevant? It's not. All right, anyway. To sort this story out, I'll first go through, well, after we're done with RG, we're gonna go through gauge theories, non-abelian gauge theories. We discuss that, and then we'll do beta function, we calculate beta functions for gauge theories, and then we'll discuss QED, right? All right. As I said, today we're going to talk about an example of Wilson-Fisher, an example which is ON model. This is a setup where we have a controlled deformation of an RG fixed point. I do recommend going back to your QED, one loop QED calculation. and seeing. I very quickly wrote down when we're doing normal perturbation theory, I wrote down the beta function for QED. Yeah. Okay. Now, theory of critical exponents. By now, I've said this several times, but I want to keep repeating it. Imagine you have a statistical system with a lot of spins. What we're going to do is that we're going to coarse grain. We're going to look at low energy excitations where we could just bunch a whole bunch of these degrees of freedom, take an average magnetization variable, and talk about the theory of that. This is like going towards the infrared. Now, if as a statistical theory, this system has a Hamiltonian, in this path integral, there are all sorts of terms in the Lagrangian density Euclidean Lagrangian density I can include. The vast majority of them are irrelevant. As you go towards the infrared, the only terms that will survive will be relevant. That is why the spin system with a very, very insanely complicated Hamiltonian in the infrared could be described using very simple physics. We don't know a piece of metal that we are dealing with. The microscopic interaction of its atoms might be insanely complicated. We have no idea how to model it. However, once you average these magnetic moments and look in the infrared, the action, you could fix it literally using the assumptions of locality, separation of scales, and symmetries. You just write down in derivative expansion every term allowed by the symmetries that are relevant. Like in expansion, of course, the very first few terms that you write down for small field and in their expansions are going to be more relevant. Good? All right. So here's your partition function as a function of the external field beta. We could calculate the connected two-point function, right? Now here comes the observation. It was observed in a lot of systems that there were some fixed points. There were in just critical systems. So we're talking about a piece of metal that's going through some sort of continuous phase transition. People observed a whole bunch of critical exponents. They saw that, for example, the connected two-point function will go like 1 over x to the power of d minus 2 plus a number. This is called anomalous dimension. If the theory was free, right, this would be 0. But people were observing critical behavior with non-zero anomalous dimensions. What does this mean in our field theory language? It's an indication of an interacting fixed point in the IR, right? When you do an experiment and you see the two-point functions showing scaling behavior with some anomalous dimension, that means that in the infrared, you have a fixed point that's interacting. So from the very basics of quantum field theory, you've already learned, you know that in higher than 4 dimensions, you're never going to see that for scalar fields. Right? Well, all the experiments were done in lower than 4 dimensions and below. For obvious reasons. So there was this eta exponent eta, which was universal, and it's only fixed. This was the universality story. It only depended on the symmetries of the system, nothing else. Different material with all sorts of crazy interactions that were microscopic interactions that were different, they were still showing the same eta as long as they had the same symmetries. This, by now, we've explained already, right? This is universality. Away from the critical point, so we can introduce this variable. So critical point has some temperature Tc, right? T minus Tc over Tc is this little t variable. The two-point function will decay exponentially. There will be correlation length, right? That correlation length as a function of t shows people who had observed showed another universal exponent, nu. Quantum field theory also explains this exponent. There were all sorts of other thermodynamic quantities near fixed points that show universal exponents. For example, the specific heat at zero external field or the magnetic susceptibility. So this was early 20th century. People were discovering that near criticality systems show these critical exponents that were universal, right? Quantum field theory, RG flow explained this. So how do you calculate these? You say in some dimensions, right? I'm just going to write down, I'm in the infrared, I'm going to write down a Lagrangian for my effective degrees of freedom. The only things I need to care about, you're just going to expand in derivatives and the small field and write all the relevant terms, right? That gives you an effective theory. Hopefully it's interacting, because if it's not interacting, then you're never going to explain anomalous dimensions. Hopefully it's interacting, right? And that action describes a low energy of all sorts of different material that show in the infrared the same physics. They show the same critical exponents. It doesn't matter what the degrees of freedom are in the UV. The emergent degree of freedom in the IR is always the same. Right? Because it's only the relevant deformation that grows. The rest are unimportant. Is that idea clear? It's a very core, it's an idea that sits at the core of renormalization group. So atomic scale Lagrangian might be complicated, but we can't care less. All that we care about are symmetries and like when you do derivative expansion and field expansion. In D larger than 4, the IR theory is massive free fields. So we're never going to end up with anything interesting. In D less than 4, people had observed these universal exponents. In particular, they had read of these anomalous dimensions, and they talked about this critical theory, this scale invariant theory that's called the Wilson-Fisher fixed point. So today we're going to explain that. Wilson-Fisher fixed point is some sort of critical behavior that people had seen, right? And it has to do with, in D equals 3, for example, say, and it has to do with scalar degrees of freedom. You don't have any other funky like spinners, right? We're going to describe that theory today using the OM model. That's what we're going to do. Are we good?
Small thing. Is there a specific reason why we only get the scalar degrees of freedom?
Well, it's just the symmetries of the theory,
Yes.
right? It's just the symmetries of the theory. What are the symmetries of the theory, by the way? So in the relativistic theory, it is, what is it? So it's translations. It's a Poincare group, right? The translations, and which is are D minus 1 comma 1. You can say it louder. And the Lorentz group, which is SO D minus 1 comma 1, right? There's this curly, this like, yeah. Now, when you go to Euclidean space, what are these groups? So it's just translations are D, and SO D comma 1 becomes just rotations. So what are we talking about? We're talking about degrees of freedom for thermodynamic theory that is translation and rotation invariant. Invariant, not covariant. It transforms trivially under these transformations, right? Once you decide your symmetries, you're in the world of scalar field, right? Good. Okay. Now, the very interesting surprise is that this Wilson-Fisher fixed point is within perturbation theory. Within the reach of perturbation theory, because I told you, I explained to you guys that if it's a strongly coupled theory, we have no idea how to attack it. Right? So this is like a success story. But it actually unveiled some sort of bizarre technique, trick, large N. Or epsilon expansion is another term for it. We'll see. Start with Lagrangian density for the ON model. What was the ON model? It's just some degrees of freedom that are a vector phi1 to phi n. These are scalar fields. This is the ON is an internal symmetry. In anticipation for the next lecture, what is the field phi here mathematically? It's you have space, which is RD, right? So this is your manifold RD. At each point sits what? Sits Rn at each point. And the action you're gonna write is rotation invariant in Rn. Right? Now, what is the field mathematically? Let's call this Rn. Let's call this X. The field mathematically is a map from space-time to X. It associates to every point in space-time a vector in Rn. Right? X is called field space or target space. M is often called space-time. But this is our choice, right? If we consider X as a space-time, that theory has a different name. It's called nonlinear sigma model. That's it. All right, but we're gonna come back to that in the next lecture. All right, so here's the ON model, right? The action we wrote down is massive. We're gonna put lambda phi 4, right? Of course, phi 4 is like to keep ON, you have to put it in this form. Because we're interested in phase transitions at finite temperature, these are statistical field theory systems, right? We're gonna give 1-point functions to phi, right? So we're gonna spontaneously break the symmetry, right? We're gonna expand around some classical value of phi classical, like a perturbation. Is that clear? Right? These are finite temperature critical points. All right, so the Lagrangian and this expansion looks like Lagrangian of phi classical plus the dynamical fluctuating field. The field with thermal fluctuation is this chi, right? Looks like this. Now, phi classical contributes to the action for chi in the following way, right? So I've written it more generally in terms of the dot product because they're both vectors. But let's focus only on the kinetic term, how it contributes to the kinetic term of this chi. The mass term is just, this is the good old mass term, but lambda phi classical squared, which is phi classical dot phi classical, right? Contributes as a mass term for the chi field. And then there's this extra term, which is not quite the mass term, but it's a term that couples chi I to chi j. Good? This is to the second order. So there, instead of a mass as a scalar, as a number, you have the mass matrix, right? Hopefully that's clear. And the mass matrix is like this. It's convenient to take phi classical to pick directions and pick it to be in a particular direction, so that this is just phi, yeah, so that this is just 1, 1, right? To simplify our life. And then call the one direction sigma and the rest of the n minus 1 pi. This is something we did before. In Fourier space, this mass matrix looks like this, right? For the what did I write here? Yeah. So the pi guys, right, only pick up this term. this 2 lambda phi squared contributes to chi, right? So the pi terms will have the mass p squared minus m squared minus lambda phi cl squared. The sigma terms will have minus p squared plus m squared plus 3 lambda, right? 2 here, 1 here. They add up. Uh-oh. All right. Charger. I should go get my charger. Sorry, all right.
When I thought it was going to be a race against time. When Ema finished the lecture, or the iPad runs out.
Actually, I'm not sure if I have my charger. All right, so let's see. What do we do with this?
Lightning or
Oh, it's just a USB-C.
I can run downstairs, downstairs or I have a USB.
Do mine actually. Sorry, because I don't have my charger. That's why I forgot. Thank you so much. Oops. Okay. So all right. So let me just summarize what we're doing, right? So I said with the ON model, right? We said that this theory is going to describe our critical point where the 1 point function of the field is non-zero, right? So what we did is that we just gave a 1 point function phi classical to the field, we expanded it, and we saw that there's we picked coordinates in the field space, right? And then that gave us the 2 sets of degrees of freedom, right? Propagating with different masses. So this is an n-1 matrix, and this is the other one. Feel bad. Oh, thank you so much. Thanks so much. I should not make this mistake again. All right, where do we? Did it work? Oh yeah, thanks. All right. Thank you so much. All right, so now recall the effective action. Effective action was. The effective action at one loop, right? We wrote it down. It was the value of the classical action for phi classical, action of the phi classical, plus the one loop contribution that we wrote as log of the determinant of the kinetic term. Right? So now the kinetic term is basically just a propagator with the mass matrix. Ln of determinant is the same thing as trace of, well, sorry. Ln of the determinant of is the trace of Ln. Right? Is the trace of Ln because determinant is multiplying, you take the log of it, it's adding, that's the trace of Ln. Good. So you should be dealing with Ln of this guy plus n minus 1 Ln of this guy. But these are differential operators, right? For every P mode, I have one of these. So viewed as a differential operator, this is, I guess, a homework for you guys to work this out. Compute this for yourself. This is not your official homework, but I absolutely recommend doing these. This will be proportional to integral of d4 of k in say 4 dimension, ln of k squared plus mu squared over m squared. I have to put this m squared to make things dimensionless. Right? I guess we hadn't computed this log determinants up until now. So we're doing it now. So you could do these integrals using all the methods you've learned. You could do it in 4 minus d minus epsilon expansion, all sorts of ways. Let me do it in a different way. They're all equivalent, right? So the way we're gonna do it is that I'm gonna write the ln as del alpha of this guy minus alpha at alpha equals 0. It's kind of like a replica trick. Okay, so then I'm gonna bring the derivative outside of the integral and evaluate it this way. Notice that now the dimension of m squared, this dimension has changed, right? So this guy is m to the power of alpha. It already looks quite similar to d minus epsilon expansion. This integral is still divergent, so I'm gonna put a lambda cutoff here. Once you put a lambda cutoff, this is the integral that you obtain. The point of this exercise is to write down the divergent terms in some MS bar scheme, right? Some minimal, you just captured the divergent terms in A1, A2, and A3, and the rest. You could do this in d minus epsilon expansion, all sorts of different ways, right? All the divergences go into these 3 terms. And the rest, the non-divergent piece is here. Good. I know it was quick, but by now you've done quite a few of these integrals. Now, the point of renormalization is to cancel these divergences. Precisely. So the counter terms are going to cancel these guys. If you don't believe me, renormalize this. And the answer is going to be basically this chunk. So it's going to be the renormalized thing is going to be phi 0, phi classical. 1/64 pi squared, this expression. This is the contribution. So let's just analyze this. This is the contribution of the pi fields, right? This is the contribution of the sigma fields. Notice the mass term here, right? And the mass term here, n minus 1 component. What we're gonna do is, of course, this is calculated to one loop, right? We just wrote down the one loop expression, log determinant. So this is only meaningful if there are corrections to this when mr squared and lambda r are not small, right? So it's legitimate to discard these at will, like higher orders terms. All right, so these are small. Good. So what we're gonna do is we're gonna take this, consider the Callan-Simanzik equation for this guy. This is the Callan-Simanzik equation. Because I have the explicit form of it, I can calculate these derivatives. It becomes an algebraic equation for beta function and gamma functions. Because on the left-hand side, I can expand it in powers of phi classical, and it's just an algebraic equation at order by order in phi classical. Right, let's pause for a bit so that it sinks in. Ooh, I'm running really behind. Let's not pause. Okay, so you take these derivatives, these are what you get. There's phi classical 4, phi classical 2, you plug them back in. This is the equation that you have. Now, there is a term that's independent of phi classical. That has to do with the vacuum energy normalization, this term. Let's ignore it for now. What you have to do is you have to bunch the phi 4 term with the phi 4 term, phi 2 term with the, phi 2 term, right? This is the algebraic equation for gamma, right? And this is the algebraic equation for beta. These are the two algebraic equations I said. Here are the solutions to them. Good. This order in perturbation theory. As usual, beta lambda is one order higher than gammas. Very good. This was done in 4 dimensions. right? There's a problem here. These beta functions are not necessarily small, right? And I don't see a fixed point. These beta functions are positive. N is positive, right? I don't see a fixed point. Now comes the trick. Go to 4 minus epsilon dimensions. Do the calculation again. We saw an example of this. Beta function comes out to be the same thing minus epsilon lambda. So there is a Wilson-Fisher fixed point when this term and this term cancel, and that is lambda star 8 pi squared epsilon over n plus 8. All right. That depends on epsilon and d minus epsilon dimensions. That sounds silly, right? Can I put epsilon equal 1 to read off, to find and interpret that as a critical theory in 3 dimensions? Can I, is that kosher? Well, one worry you might have is that why did I need small epsilon? Perturbation theory, right? Because small epsilon tells me that lambda star is small, so I can trust my perturbation theory, right? This was calculated in small for small lambdas, right? There are higher order corrections. If epsilon is not small, I'm not guaranteed the cancellation, right? But what if epsilon is 1, but n is large? Then you could trust your perturbation theory. This is called the Wilson-Fisher fixed point. It actually calculates for you things that we want. Now, this is the start of a large set of theories we could construct, right? Here, what we talked about was ON scalar fields. Let's make it a little bit more interesting, right? Let's talk about all sorts of different fixed points we could have. But the principle is going to be similar. Notice that what allows me to control these calculations is large N. If N is not large, I have absolutely no control. There's no justification for this at all, right? So one important lesson, no matter what the underlying physics of these dirty tricks are, one important lesson is that quantum field theory at large N simplifies. Do you have a guess as why that should be true? If you have the action for a scalar field, right? You put it in it's e to the power of is. If you have n copies of a scalar field, non-interacting, not related, the action is going to be n times the scalar field. Now you have the method of, you can use stationary phase approximation, or if you're in a statistical field theory, for large n, you could do saddle point approximation. That has a name in physics. That saddle point approximation is called mean field theory. If you ever hear mean field theory, that's what it is. This large n is mean field theory. Interestingly, you could do 1 over n corrections to it anyway, and then put in back the things that you got rid of. All right, so a lesson here is that there's this Wilson-Fisher fixed point that we found that is kind of cool. You could calculate gamma phi squared minus n plus 2 over n plus 8 epsilon, set it epsilon equal 1. You could calculate these critical exponents. They come out right. It's nice. Now, large n, we talked about ON model. ON model has a large global symmetry. Large n techniques are useful in gauge theories as well, where there is no global symmetry, but there's a redundancy of our description. They're actually extremely useful for gauge theories. We'll see that. All right. Okay, now I'm gonna say 2 more examples of these perturbative fixed ones. So Wilson-Fisher fixed one was an RG flow between two fixed points, UV and IR, the whole thing was controlled within perturbation theory. Right? That's kind of nuts, but it's a good example. Let me give you two more examples. Actually, one of them I'm just gonna say in words. I'm not gonna mention anymore. But the other one, I'm gonna say a few more words. There's another one that's called Banks-Zaks fixed point. So we're gonna come back to this when we do beta function for gauge theories. But this is a theory. I can just describe the matter content to you classically. Hopefully you remember part one of the course. It's SUNC, non-abelian gauge theory. So NC is the rank of the gauge group, SUN, right? And then I have fermion fields in the fundamental representation of the gauge fields. And I have NF copies. I haven't told you how to calculate this, but you could calculate the beta function, comes out this way. What is G? G is the coupling of the super Yang-Mills. Do you remember how it was defined? 1 over G squared trace of F minus, right? So this is beta function for G. It looks like this. There is a G3 term with a minus sign B0 plus B1. So there is G star, which is a fixed point for B0 over B1. So what are these values of B0 and B1? You could write them down in terms of NC and NF. The only thing they depend on are just NC and NF, and they come out this way. So there is a range of NC and NF where you have a G star, where you get a cancellation. And again, this is a perturbation theory calculation. So you have to make sure the cancellation occurs when G is small, right? You could also arrange for that. And these are called Banks-Zaks fixed points. There is yet one more example. There is one class of examples that I want to mention. There are theories where, so here the problem is we wanted to do perturbation theory, perturbative calculation of beta function, because that's all we can do. And from that, we wanted to deduce zeros of beta functions, right? Now, there are a class of theories, supersymmetric theories, where because they're so symmetric that certain one loop calculations are exact. You could prove that if you calculate beta function for some coupling, particular couplings, then those are only one loop. They stop at one loop. There are no other higher corrections by symmetry. Some symmetry. Recall that like the only thing that could help you save you is symmetry, right? In the absence of symmetry, the world is as bad as it gets, right? So if there's symmetry that forbids it, like in certain supersymmetric theories, people calculate these coefficients, these beta function to one loop, or they could show that they cancel in certain setups. So there are non-perturbative fixed points we found in these supersymmetric theories based on one loop calculations, right? So those are, if you wish, if you're asking, do we know any non-perturbative fixed points? Yeah, the theory is very symmetric. There are some examples of that. All right. So in summary, what did we do today? We first went back and made a little bit more connection between these critical exponents of statistical field theory, these anomalous dimensions or universal exponents we were seeing near continuous phase transition in a statistical system, right? And the idea of low energy quantum field theory, right? So if you are in less than 3 dimensions and you have a piece of material that shows critical behavior and you're reading off a bunch of exponents that are anomalous, right? You say, okay, I'm going to write down all the relevant terms I can write down, right? Assuming symmetries, and can I cook up a theory that shows a fixed point with those anomalous dimensions, right? This is why field theory is so powerful. All you need to rely is locality, symmetries, right? And the idea of separation of scales. Why separation of scales? Because you write down it's possible that you have to keep adding irrelevant terms, right? If there's some physics nearby that you're missing, right? That you recall. But if you're sitting near a fixed point, you're good. Near a fixed point assumption gets rid of that. Good. So then we give examples. We give examples of this. In particular, Wilson-Fisher fixed point. I want you guys to keep that in mind. So even though we use d minus epsilon expansion up until now as a trick to get rid of our divergence or regulate our divergences in MS bar scheme or whatever we're doing, right? There's also another aspect, another place where it could help us understand things better. And it's in the context of calculating beta functions in d minus epsilon expansion. We could end up with fixed points for small epsilon, right? Now, if I take epsilon to be 1, not small anymore, but somehow arranged for, in this case, by large n, for perturbation theory to still hold valid, then I've actually done something significant, right? And that's the story of Wilson-Fisher fixed point. There are other examples of this in physics, but in general, the rule of thumb is that if there is no symmetry, like supersymmetry or some crazy principle that tells you that some perturbative calculation is exact, you are sort of stuck within perturbation theory. And usually the way we arrange for these perturbative fixed points is by a large number of fields in gauge theories, and like you have flavor, gauge, like the degree of the gauge field, the SUN of the SUN. And this is a trick we use in physics. As I said, it's very important for us to discover fixed points. Quantum field theories are perturbations around non-trivial fixed points or trivial fixed points. But all right, so that's this. Are there any questions?
Like, for example, over here, for the Banzas, I see that they change sign and that's how we get this one. In the beta function. Like there's a minus, negative term and minus plus.
You're saying that if you go to higher orders in G7
No, for the OM model.
for the ON model, okay? Yes.
Like if I produce say on lambda Q, lambda.
In D at D equal 4.
Yeah.
All right. There won't be a fixed point. Why? You already know it. We did that. We already said the lambda 5, there are no relevant terms for scalar field theory in the equal form. There are no non-trivial theories. Right? Yeah.
Okay, as you were saying, like in SUSY, we calculate this non-perturbative fixed points.
There are examples where we can.
Okay, like there this beta function trick doesn't work, right? Because we assume that, or does it work? That's my doubt.
Which trick?
Like we said that the zeros of the beta functions were giving me the fixed points. Right?
Yes.
But that was for the perturbative regime, like small lambda.
No, zeros of beta function always give you fixed points.
Okay, so that
Now you calculate beta function perturbatively,
yes.
right? That's the thing. So if you are not guaranteed that the beta function, the full answer is going to remain first order or whatever order you have calculated, then right? But zeros of beta function is something Callan-Simanzik holds, period. As a matter of fact, 2 lectures from now, when we do the non-perturbative RG, so what's called ERG? Exact RG. The story of exact RG is just saying, let's forget about perturbation theory altogether. What we're gonna do is that we're just gonna formulate the idea of a normalization group as these like ideas, as a bunch of equations for the flow of couplings. The same way we did for we had this discussion of integrating momentum shell. So exact RG is a more formal way of doing that, which is more rigorous. And it makes certain things clearer, right? But if you're dealing with exact RG as you don't have perturbation theory tools, but then usually we use large N. So exact RG becomes sort of manageable in large N approximation. Good. It's another perturbation theory. It's not a perturbation theory in coupling, it's a perturbation theory in. All right, any other questions?
Taking Lachlan rings must be equivalent to the scale of the constant H bar.
Sorry, there is no time constant here because these are non-gravitational theories. But you're asking is the H bar, yes, yes. Yeah, because remember, yeah, H bar was being small was the justification for saddle point approximation for stationary phase approximation, right? Now here you have an N parameter. It's not, sorry, let me clarify this. It's not. Yeah, it's not. Yeah, that's not, I think the argument I just said is a little bit too quick. So what we usually do is, as you saw, I write down my Lagrangians without H bar in them. Right? What have I done? What I have done is I've absorbed the H bar of the kinetic term in the field redefinition. That makes the idea of phi being quantum fluctuations being small. Right? Quantum fluctuation being small is that I've eaten phi, H bar in phi. Now, as I expand to higher orders in phi, my interaction terms will have H bar in them in a sense. Right? I've set H bar equal 1. When we say we set C equal 1 and H bar equal 1, right? What it means is that H bar has gone into the coupling. The coupling, like the size of fluctuations is controlled by that. Right? So when you say you're non-perturbative, there's a sense in which H bar is no longer small. Right? So N plays a role of H bar, a new expansion parameter for you. It becomes a new expansion parameter. All right, any other questions? This is also the sort of gravity actually, but yeah, N of SUN is like becomes related to gravity. All right, if not, thanks so much.